Hello everyone, you can hear me? Okay. My presentation name called Behind Enemy Line, Reverse Engineering C++ in Modern Ages. My name is Gal. I'm a security and vulnerability researcher. I do a lot of reverse engineering, and specifically reverse engineering for C++. I also like to play the clarinet and sew clothes. And this is my Twitter handle. So we are going to start with binary creation. Whenever you have a source code, you have the compiler, the linker, and then it creates the binary. But what if we would like to reverse the process? If you would like to go from a binary to a code. So the process is called reverse engineering. There is some difficulties that happens when you do reverse engineering for C++ code. So the first is that local names and types don't appear in the binary, since after compilation you cannot have all of those things. Unless you compile in debug mode, and then some of those things create symbols, and then you can have partial names and types. One more thing is that optimization that the compiler does is kind of very complicated when you look at the binary afterwards, because there is a lot of stuff that are very complicated to understand. If it's like the user who wrote the code and this is the reason it looks like that, or was it the compiler who is responsible for this behavior? So it's something that with time becomes more and more clear. The other thing that I want to mention is static and dynamic analysis. Static analysis means that you have a binary and then you look at the code without executing it. So you look at the assembly and all you do is understanding the logic without executing. Dynamic analysis is executing the code and then look at the assembly while it's being executed and understand the logic from there. One more thing I want to mention is that there is also hardware reverse engineering. This talk is going to focus about software reverse engineering, but also hardware is something you can reverse engineer. You can understand how a board looks like and stuff like that. But our presentation will focus on software. So what is it good for? There is many purposes for reverse engineering. The first is vulnerabilities. Whenever you have a binary and you want to understand and find vulnerabilities, sometimes when you don't have the source, you need to reverse engineer, find bugs, find vulnerabilities, try to exploit them. And this is one thing you can do with reverse engineering. The second thing that you can do is to understand the logic of a code or an algorithm in order to understand and solve complex problems like synchronization, optimization, and stuff that you probably know from your day-to-day job. So the reverse process, what happens is that you have a binary, then this assembler can create assembly code from the binary. Afterwards, you have a decompiler and a human. The decompilers that there are today are mostly compatible with C, but with C++ there is still a lot of problems that happens with decompiling code. Specifically, you have all the polymorphic classes, and also you have the virtual calls. It's very hard to create a correct and full decompiled code. So you always have to go over everything by a human. So the work is with the decompiler, with the decompiled code and the assembly all together. And what is the most effective way to learn reverse engineering of C++? You would all answer, of course, playing Chicken Invader. But the problem is that I'm not really good at that game. I can't win without cheating. So we are going to use the knowledge that we have in reverse engineering in order to win the Chicken Invader game. So what do we have? We have a binary of the game. We have the tools for disassembling the code. We have our knowledge in C++, and we have some knowledge in reverse engineering. Our tools for reverse engineering are Ghidra, Radar, Binary Ninja, and IDA Pro. Specifically, we are going to use IDA. This is my favorite tool, and also it's very comfortable to work with IDA. So assembly basics. It's specifically for MSVC compiler, because this is what we are going to see during the talk. So first we have the important registers. The important registers are RAX and EAX that stores the return value of functions. Whenever you have a function call, the value that returns from the function are going to be stored in RAX. I will mention also that the differences between RAX and EAX is that RAX is the x64-bit register and EAX is the 32-bit register. So it's also depending on the architecture that the code was compiled to. The second register that is important to know is RCX. It stores usually the pointer to the object. This is specifically for MSVC, but we are going to see that a few times during the talk. One more register is RSP. RSP is the stack pointer. It points to where we are on the stack. EBP is also one of the registers that it's important to know. This register stores the pointer to the base of the stack frame. Another last thing is that MSVC fast calling convention. So it uses registers to pass the parameters to functions. So when it is possible, it's also important to know that there is some types that cannot be passed through registers. For example, unique pointers and share pointers will be pushed into the stack. So these are the registers that are being used when a fast call is being used. And after all the register is being used, and other parameters will be pushed into the stack. Okay. So now after we did a small introduction to reversing and what we need to know about MSVC compiler, so now we are going to start and understand about reverse engineering of C++. So we are going to start with dynamic. Okay. Okay. So first we are going to start with dynamic object creation. This is a simple code that doesn't do much, but it's a class named person. And at the end, you have the main. The most important part is this line, the creation of the object. The first part is the new that calls operator new. And the size is the parameter that is being given to the function. I will also mention the weird name that you can see there. You can see like a GZ underscore and operator new. The reason is the GZ is my initials. And whenever I change the name of a function, I add my initials in order to see the differences between symbols in binaries and the functions that I changed. So this is when you see during my slides that there is a GZ in the beginning of function names. This is because this is a name I changed. The second part is person. Person is like the calling for the constructor. Also in here you can see my initials, but with first letter J. It means that the function that I changed, that was a GZ person constructor, was wrapped by a function that just called it, which is a jump function. So in order to represent it, IDA, the disassembler tool we use, add J at the beginning of functions that just call another functions. But what you can see here is that the person is, there is a function call to the constructor of person, and the value that is stored in RAX, it's the return value of this constructor, is being passed to a local variable. So now we are going to focus more about the constructor itself. So we have a few ways to recognize a constructor in assembly. The first part you can see is the vtable assignment. So in a lot of cases, when you have a vtable, also this is not like if you don't have virtual functions and the class is not, don't have to use the virtual function, so there will be no vtable. But in this case, you saw that there are 3 functions that were virtual functions in our class. So in here we have the assignment of vtable to the first 8 bytes of the object. The second part is the parameter. You can see that in the age, the private parameter that the person class has, is moved to the offset 8 from the beginning of the object, which means that because the vtable is in the first 8 bytes, so the members will come afterwards. So in this case, it's after after offset 8. Okay, so virtual calls. This is a main part for reverse engineers to understand virtual calls because they are very complicated in assembly. What happens is, for example, you have that code. This is like a source code of a virtual call. You have the virtual function, and also you have the virtual call itself. But in assembly, what you have is that first you can see the move of the virtual table to REX. Second, we can see the virtual call itself. In this case, you can see that the call, what happens there, is that keyword PTR with the brackets means that you take the value of the register that's in the brackets. So in this case, you have RAX plus 8, which means you take the vtable and you use offset 8 from the vtable, which means the second function, since we are in x64-bit architecture. It was compiled to x64 architecture. Okay. So we covered so far, we know basic knowledge in assembly. We have the dynamic object creation, the basic constructors that we covered, and also the virtual calls. So after we know all of that, we can go into the reversing of the game. So strings in the binary. First thing that most of the reverse engineers do is that they look at strings. Strings are very simple, they are human readable, you don't need to go straight to assembly before you look what you have in the strings. So every time you have a string, you can just press X with IDA, our tool, and see where the string was called from. So in our case, you can see you won the game. This is kind of an important string for us if you want to win the game. And we would like to see where it was called from. So you can see it was called from a function named controller run level. So the second question you might ask yourself is like, why do we have names? Before I said there is no names. So this binary was compiled with debug symbols. And for that reason, I can see the names and I can see partial types. So during the talk, it will be easier to explain the concepts, but usually you don't have names, you don't have all of the things you might think it's a bit weird. I will mention each time you have those things that created by debugs in the code. So, controller run level. This is the function that the string was called from, and we are going to focus first on the spaceship. In the beginning of the function, I saw there is a shared PTR to a spaceship. You can see again the reason that I have the name and I can see that it's a shared pointer is just because the code was compiled and debugged. So we are going to take a deeper look at this object. First, the constructor. We already talked about constructors before, but now we are going to focus about this weird behavior. You can see there is a call for the game object constructor, and afterwards you have an assignment of a vtable, spaceship vtable, into the first bytes of the object. You can see that RCX, as I said, is usually the pointer to the object, and this is what you can also see there. So we would like to focus more and understand why there was a call to game object. Some of you might guess by now that, but we are going to see that more in deep we can see it next. Spaceship vtable. So this is the spaceship vtable as it is represented in IDA. I know that you might see vtables a bit differently, but in this case, this is how IDA represents it. So the weird thing is that you have many functions from game object, but only one from a spaceship. The name of the function is a move object, and it contains, and as I said, it contains both game object and spaceship. The reason for that is that spaceship actually inherits from game object. This is why we saw a constructor call inside the constructor of a spaceship. There was a call for game object constructor, and also this is why the vtable combines both functions from game object and from spaceship. So we would like to understand game object a bit more before we continue. So the vtable of game object, in the constructor we can see that there is an assignment of the vtable to the first bytes, 8 bytes of the object. Afterwards, we can see the member initializer. You can see a call for get desktop mode. The return values from the function are stored in EAX and then moved to the relevant offsets in the game object. The reason that you can see that EAX is the register that we use is because the return values are integers, which means that although we are using the x64-bit architecture, so we still need to use the 32-bit registers in order to pass values that are smaller than that. In this example, integers, which are 4 bytes. Okay, so this is another representation of the vtable of game object, but this one is more similar to what we saw before. So you can see that here you have a pure call in the vtable of game object. Again, you can see the J in the beginning of the pure call, which means the pure call was wrapped with a function just called a pure call. So what does it mean is that if we want to recap what we understood so far, because the reason we have a pure call is exactly why we saw in Spaceship that there is a move object function that was unique to the Spaceship. So first, if I understand from all the assembly that I saw, I could write like some kind of a pseudocode. So this is the example of the pseudocode. You can see the class Spaceship. It inherits from game object. It has one virtual function that is move object that it implements it. And the second thing is the game object. I just copied the names that I saw in the assembly. And also I added that the pure virtual call that we saw was actually a move object pure virtual call. But now I have the name because I could see the name from the class Spaceship. Okay. Code flow. So what we're going to do now is look at the code of come back to what we saw, the controller run level code, and come back to the function and understand what happens there, because this is the function we understood so far that is the important one. So first we can see that there is, after the Spaceship shared pointer, I saw that there is a call to fill waves vector. So the name and the purpose are quite similar. What it does, it begins with creating a vector, and then it fills it with wave interface derived classes. In this case, the class is a wave2. You can see that the wave interface was part of the vector in the first line, and wave2 is the class that is being used. So we can assume that this is one of the derived class of a wave interface. Okay, so what more did we have? After looking more at this fill waves vector function, I could see that there is a wave boss call. So it means that one of the classes that were used, one of the elements in the vector was a wave boss class. So in this case, I will do a small, okay, I will come back. Wave boss is quite important for us because what we wanted in the beginning is winning the game. And wave boss is probably, I will assume, is the big chicken boss that you need to fight and it's like impossible to pass. And this is like my assumption, but we need to check it and look further in order to give like a concrete answer. So if I'll summarize it, the fill wave vector function from the assembly, I could realize look something like that, just in place back the objects, and that in general how it looks like. Now we can come back to one level. This is the main function we looked at. It was the function that also called the string, the one that called the fill vector, and what I saw there is that there is a virtual call. So there is many problems when reverse engineering C++ code, but when you have a virtual call, it's like a major one. Since we don't always have the ability to dynamically reverse code, so you need to statically understand the flow in order to understand what was the virtual call. And this is like a very hard task to do. So in any case, you can do dynamic analysis when you have a virtual call. This is what you do. So this is what we are going to do now. We are going to go to our easiest solution. which is dynamic analysis. So you have an ability to add a debugger to IDA and debug the code, the assembly code that you have. So in our case, I placed a breakpoint on the virtual call. You can see it in there, and we can see in the right side, you can see that there is the registers that I talked about and some more of them. And RAX stores a value of an address. So now we can go into the address and see what happens there. So we can see that the virtual calls is to wave3 create wave. You can see the offset, the address is to a vtable, and the offset is the create wave function. So now we are going to look again at the virtual call just to show you that it happens again. Again, you have an address, and in this case, it's wave4. So each time you have a virtual call, what happens is that a create wave function is being called, depending on the object. So we know that this object was part of the vector. So after looking a bit more, we saw there is it iterates over the elements of the vector, and then choose the relevant object and call the virtual call, use the virtual call and call the create wave. So after a few iterations, I arrived to the stage when I'm supposed to deal with the boss. And when I needed to deal with the boss, I looked what happened in the assembly. I again stopped in the breakpoint and saw that the wave, the object that is being called is wave boss. So now we have like a concrete understanding that wave boss is the object that's responsible for the level with the boss. So examine wave boss 2. You can see an example of the boss. Okay, wave boss constructor. So first we have what we learned so far. We have the vtable, it's being stored in the first bytes. Then we have some member there that is, the number is 15, but we still don't know what is this member, and we will need to have further checks before we decide what to do with it. So from here we understand that wave boss, the vtable, if you can see, is the vtable of chicken boss and not wave boss. The reason is that because chicken boss inherits, wave boss inherits from chicken boss, and the wave boss doesn't implement new functions, so it can use the same virtual table. Okay, oops, sorry. Okay, so now we want to know what exactly do we want to change in order to win, because this is our main goal after learning reverse engineering. So the process, I'll summarize it because the process was quite similar to what we've done so far. And I'll summarize what I've done and what I figured out. So chicken boss is the base class for a wave boss. But there is like a full inheritance you can see. Wave boss inherits from chicken boss, that inherits from chicken base, that inherits from game object, as we already saw before. So game object has many children. So it has like regular chicken and spaceship, and I could come back after understanding that this is like an extremely important object. I can come back and understand more stuff about the object after the process I've done. So I understood that one of the parameters in the game object was the number of lives that an object has. So this weird number that we saw, the 15, is actually the number of lives the boss have. So now we want to change the amount of life because 1 is like enough for us. We just need to shoot it once and it will, and we will win. So this representation, you can see both the assembly and the hex representation of the instruction. So you have here the number 15, which is represented by 0f00000. We will change it to 1, which means we patched the binary and now we have a new value. And now we can, just run the game, shoot the boss 1 and win. And just when I thought it is over, I arrived to the scoreboard. So what happens in the scoreboard is that I wouldn't be able to enter my name before because I wasn't good enough to to succeed. Now I saw that I'm good enough. I could enter the scoreboard. I am able to enter my name. And if you can see, there is like a small line at the top left that says, well done, congratulations. So every time you enter to the scoreboard, a new message appears. It can be hooray, first place, well done, congratulations. It can be like lots of things, but it being randomized every time that you enter a new score. What happens is, one time I entered my score and this is what happened. And this is not any string that I would assume supposed to be there. Like, it's my name, 3 dots, and the score, which is a bit weird. You can see that there is the same score and name in the scoreboard. So I was like, okay, this is interesting. Let's dig in and see what happens and why. So first I looked at the Scoreboard function. So this function actually is responsible for choosing the strings for this sentence. So it chooses from 2 strings, 2 global strings, concatenate them, and then call the allocators for each one of them. Before we go into what happened, I will explain a bit about small strings optimizations. So in MSVC, which is our compiler, what happens is that it checks if a string is smaller than 15. You can also see the assembly lines in that shows what happened. It just compares the value to 15, and if it is smaller than 15, it goes to a branch that stores the string on the stack, and if it's bigger than 15, it allocates the string on the heap. It is also important to say that different compilers has handled it differently, and I'm not going to get into it now, but like what happens is that, for example, GCC also use a size of 15, but Clang use 22. Okay, so cheers. Cheers is the first string that was used for our sentence, or what was supposed to be our sentence. You can see that in the assembly you have cheers. The string length is 8. You can see it being stored in RSI. The source of this is a global string that is cheers with an exclamation mark. And also you have the destination in an address on the stack. So this is the first thing we had. We have the cheers. We saw that is being stored on the stack. The second thing that I saw was hooray. Hooray is also being stored on the stack. It's very similar, the process, to how it looks like in cheers. So I'm just going to move on and show you how the stack looks like. So you have cheers and array both on the stack. You can see in the right how the stack looks like approximately, and also on the left like how it looks like when I debug the code and look at the stack. So allocating a new winner for the scoreboard. So what happened is that after I won, I could enter my name, and the score and my name was appeared in the scoreboard. So what happened in the part that's responsible for that you have a function call that what it do is like get the name that I entered and creating the string of my name, the 3 dots and the score, and then call the allocator for it. What happened is that the address for the allocator is the same address on the stack that cheers and array had. I don't know if you remember, but this like memory and this value specifically was the same address that was used for using the cheers and array string on the stack. So if you want to examine the stack before and after the call, so you have before you have the cheers and array. You can see again the stack, and afterwards you have the gal and my score on the stack in the same places. Okay. So this is weird, but now we have more understanding of why and what happened there. So what we figured so far, that you have 2 global strings that are being concatenated and can be stored on the stack or on the heap, depending on their length. And also you have the score and the name that is also can be stored both on the stack and the heap, depending on the length again. But the big question that all of you probably have is that why? And like, why the code? What is the code behind it? And why is this weird behavior happens? And the answer is string view C++ 17. What I figure out, there is a previous talks that was explaining about this situation. You have a Victor and a Nikolai talk. So if you want to get deeper into understanding why and how it happens, you can watch the talks. They also have reference to other blogs and a presentation you can watch. But in general, string view is implemented like this. You have a size and the pointer to the string of the string view that the string view uses. But string view doesn't own the memory, which means that it has no control over the object's lifetime. Which means that in our case, the return value from the function created a dangling reference. And we could actually write other stuff because there was a dangling reference from misusing string view. So the pseudocode. In order to make it clear, I wrote what I thought is the pseudocode. This is like what I saw in the assembly. I could figure out approximately how the code looked like. So first I wrote like some of the strings I saw in the global strings. That was the sentence in the scoreboard. Well done, first place, all of those strings. Second, you can see a function that concatenate two strings and store it in a string view and then return the value. Afterwards, you can see that there is the function call from main. And after this function call, you see the function that's responsible for creating the gal, 3 dots, and the score, the string that actually overwrite the string view return value from the function. So this is how approximately it looks like. It's all based on like what I saw in the assembly and the understanding of the flow, understanding of the objects that I saw there. And this is how you can actually see assembly and create a code only by looking at what the binary can reveal for you. So if I want to summarize everything, I want to give you what do you need to get from my talk. So first, reverse engineering can explain a program to the smallest details. You can see everything that moves from one place to another. You can see all the flow. So actually, reverse engineering is a good solution for understanding specific stuff in programs. Also, reverse engineering, as you saw, specifically for C++, is very complicated. You have a lot of difficulties you will see when you start reversing. And this is one of the things I wanted to show in this talk. Another thing is that you can understand a lot. As you can saw, we understood a bug, and we could also overwrite the bug with our string only by looking at assembly. And there was no source, only assembly, and we could still understand those small details and figure out how the program looks like. And the last thing is that always think that there will be a reverse engineer at the end that will look at the code, try to find bugs, and exploit them. And if you don't know for 100% what will happen with your code or what will be the cause of some action, so it might have severe consequences at the end. So always think that there will be an evil person at the end that will try to do malicious stuff on your code. So know what you're writing and try to make it as clear and as clear as you can. So thank you for your time. Is there any questions? Yes.
Okay, I've got two questions. I have noticed nope mnemonic, the command. What is the use of it, if you can tell me? Because
what do you mean the comments?
No, okay. In the code, in one of the first slides when you've shown me, no operation.
Like the first slide?
One of the first. Even before. Oh, here. Okay. Second. What was the reason it's there?
What comment? You mean like the vtable?
No, no operation.
Sometimes the compiler adds nops in the code. It does nothing, like not like
yes.
but it's part of the compiler. Just like sometimes you can see that the knobs being added, it's part of the compiler optimization.
Alignment, but
Yeah.
it's alignment. Okay.
Yeah.
Okay, it's not only data needs to be aligned, but functions as well, right?
Yes.
Okay, fair enough. Okay, another thing, I know it's not the only one, but still it's not clear for me about this J prefix. If it's only me, then don't bother, but...
So the J prefix, I will
Yes.
show one of those. We'll go back. We will go a lot back. Okay, like this. Okay, so what happens is sometimes the compiler creates the function, like our constructor, for example. We have the person constructor, and in order to, and then the compiler creates another function that all it does is jump to the function. Just
Why does it jump directly?
I can't give you like a specific answer for why, but it happens. Like sometimes, specifically when a code is compiled to debug, in release it doesn't happen that much, but in debug, it has like one function that inside, all it does is calling a different function. And IDA, the disassembler that we use, can recognize that this behavior is something, is a pattern. Just add a J, which is a jump, and the name of the function. So I change the function inside, but another function can just call, and all it does is calling the function. And this is why a J being added. Okay, is it clear now? Okay. Another question? Okay, thank you very much. If you need any other questions, feel free to contact me.